Today, students, we're going to carry on where we left off. In the previous lecture, I did show you how to reduce a system of equations into echelon form using Gaussian elimination. But in the previous lecture, we dealt a lot with 2 by 2 matrices. We never got to a 3 by 3 matrix. So in this lecture, we're just going to use Gaussian elimination. Just note that Gaussian elimination is used to reduce the system into echelon form, whereas Gaussian Jordan elimination is used to reduce the system into its row canonical form. What row canonical form is that if a matrix, a matrix is said to be in row canonical form if it is in an echelon matrix and satisfies the properties below. Each pivot that is a leading non-zero entry is equals to 1, and each pivot is the only non-zero entry in its column, which means it looks more like an identity matrix. So row canonical form is an additional property of an echelon matrix. So if a matrix is in row canonical form, is already in an echelon matrix, but an echelon matrix cannot be in a row canonical form. So there's an example here that we can use to solve, that we can use Gaussian elimination in. First, we can use Gaussian elimination if the system is not reduced, is not in a matrix form. For instance, in this case, we use the first equation because its coefficient is 1, so it will be very easy to eliminate x, right? In a sense that in order to eliminate x, we just multiply the first equation with -12 and we add the second equation. So it will yield -12x and 12x will be 0. -12y and 2y will be -10y. And -12z and -3z will be -15z. 12 times 0 is simply -12 times 0 is 0. 0 plus 5 is 5. So in order to eliminate x in the second equation, we multiply the first equation with -3 and add the third equation. And that equation, the operation will yield 0. -3x plus 3x will be 0. -3y and 4y will be y. And -3z and z will be -2z. And -3 times 0 is just 0. We add -4, it will just be -4. So once our system is in this form, we have -10y minus 15z is equals to 5. So it means that we multiplied the third equation with 10. So L3 now changed to -10, right? -10y, and then we added back L2 to get the third equation. It's just that it's not in one slide, so it's not it's not clear. So what we did here, we said 10y and -10y will be 0. -2 times 10 will be, -2 times -2, -2 times -10. No, we just multiplied by 10, not -10. -2 times 10 is -20, and we add -15 to get -35z. And this will be -40 plus 5 will be -35. That's how we got this third equation We got it by multiplying the previous third. We multiply this equation by 10. So L3 is just 10 L3 plus L2. That's how we got to eliminate Y. We say Gaussian elimination because we keep on eliminating the variables. Obviously, if this system is in this form, we just have, it's easy to solve for Z, because in this equation we have one unknown and one equation. So negative 35Z is equals to negative 35, which means Z is equals to 1. Once Z is equals to 1, we use backward substitution to solve for Y. Negative 10y minus 15 times 1 is equals to 5. Negative 10y minus 15 is equals to 5. I take negative 15 to the other side, I get 20. So y is just negative 2. I have y and z, I can use backward substitution to solve for x. So x is 1 minus 2 is equals to 0, which implies that x is 1. So this is how we use Gaussian elimination to solve a system of linear equation. In a test setting, you can just get this in a matrix form and reduce your and perform your operations on a matrix row. It's still correct, even if you take a matrix and operate and perform row operation in your matrix to solve for your variables. So we have another system here, right? So we can row reduce our matrix to echelon and canonical form. So when we say row reduce, it means that, for instance, if we take this matrix here in number 1, we can actually, if we take the system of linear equations in number 1, we can write it in matrix form and row reduce it into echelon form and canonical form using Gaussian elimination. So we will do the first example. As with the second example, I will leave it as an exercise. It will be it will form part of your online assessment. I will not do it in class. So what I did with my matrix, my system of linear equation, I just wrote it into an augmented matrix form, as you can see, right? So my system, as I took it from the previous equation from number 1, I write it in matrix form to get this matrix here. But then I don't like to deal with fractions. The reason why I interchange row 2, why row 2 becomes row 1, is such that I don't deal with fractions, because they can be a little bit tedious and confuse you and give you a wrong solution. Not that it's wrong, but it's easier not to deal with fractions for the sake of mathematical convenience. So row 1 also changes, it becomes row 2, right? And then our resulting system is this one. So once my system is in this form, as you remember, we did allude to your pivot variables or pivot entries. In my matrix, my pivot entries are 1, 2, and 3. And my objective, in order to reduce my system to echelon form, is to get every entry, or within a column of a pivot, I want to make sure that my pivot, everything under the pivot is 0. For instance, in column 1, my objective is to get these two, to get 2 and 2 to be 0, right? And for this entry here, my objective is to get this to be 0. Obviously, 3 is my last pivot and there's nothing underneath. And once I get to 3, I stop. So in echelon form, the objective is to get the entry below my pivots to be 0. So what I'll do in this case, my pivot entry is 1, right? So row 2 should change. So I pivot with respect to this entry here, the entry which is in column 1 and row 1, right? So what's going to happen here is that I multiply the first equation by -2 and I add back row 2, right? If I do that, -2 plus 2, obviously row 2 changes, but row 1 remains as is. -2 times row 1 is -2 plus 2, I get 0. -2 plus 2 is 0 again. -2 times 1 minus 1 is -3. -2 times -2 is 4. I add 0, I just get 4. So row 2 changed. I changed it with these equations. You guys must remember that these operations are quite important because they give me an idea on how you got to here. So it's very important to make sure that these operations are clear. And row 3 should also change. Normally I like to put row 3 next to row 3, but because of the program that I use to write these solutions, it only allowed me to write it that way. But I would prefer this row 3 change to be next to row 3 itself. I just wrote it this way because of the program. Otherwise, if I wrote it by hand, it was going to be just next to row 3. So what happens is row 3 will change and it will become -2 row 1 plus row 3. So what's going to happen is -2 row 1, -2 row 1 is, I'll get -2. I add row 3, I get it's -2 plus 2, which is 0. -2 plus -4 is -6. -2 plus 3 is 1. -2 times -2 is 4. I add 0 to get 4, right? So what happens here, you can see that this system here is not yet in echelon form, right? So we did point out that you can interchange rows when you perform your when you operate on equations of linear system. So in this case, to get my system into row canonical form, I need to interchange row 2 and row 3. So what happens is that row 2 becomes row 3 and row 3 becomes row 2 to obtain the system below, right? So what happens is that this system, as you can see, is an echelon form, in a sense that in the column, everything that's within the column of a pivot entry, everything that's underneath the pivot entry is 0. My pivot is -6, and under -6 we have 0. My pivot is -3. Under -3 we have nothing, because this is just the system of 3 equation. As you can see, this system is in upper triangular form. So it is in echelon. It is in echelon form. And once our system is in echelon form, what we can do is we can use backward substitution to solve for z, y, and x. But we did talk about row canonical form. If our system is in echelon form, it means that we need to perform more row operations to get it to canonical form. And once our system is in row canonical form, you can simply read off the solution on that matrix itself. And the most important thing is that the solution of your row canonical form should be the same as the one you obtained with backward substitution from the system that was in row echelon form. If that is not the case, it means that you've made a mistake somewhere and you should go back, retrace your steps and see where you made a mistake. So we use backward substitution here. As you can see, all these equations are from our matrix that's in row echelon form. So negative 3z is equals to 4 as per this equation, as per this matrix here. This coefficient negative 3 corresponds to z. Negative 3z is equals to 4, which implies that z is equals to negative 4 over 3. And negative 6y plus z is equals to 4. This row corresponds to negative 6z plus y is equals to 4. So we have it here, negative 6y minus, okay, why do I have, okay, but it will give me, this should be negative 6 plus y is equals to 4, which means here we should have negative 6y plus, not negative, plus minus 4 over 3 is equals to 4. So what you need to do is to change this to plus and bracket this. If you can just take a note of that, this should have been a plus, right? So all in all, we have negative 6y minus 4 over 3, and when I take this expression, this plus minus 4 over 3 to the other side, I get a positive, right? So negative 6y is equals to 4 plus 4 over 3. I simplify it further to get y is equals to negative 8 over 9. I have my y, I have my z. I substitute back into the first equation, which is this one here, x plus y plus z is equals to negative 2, which is this equation. With algebraic manipulations, I arrive at x is equals to 2 over 9, right? And now this system is already in echelon form. If it's in echelon form, I can reduce it further to canonical form in order to read my solution of the matrix. So as we have already alluded to the fact that in order for our matrix to be in row canonical form, all the diagonals should be 1. Right? All the pivots, actually, not necessarily the diagonals. All my pivots should be 1. And in every column of the pivot itself should be the only non-zero item within its column. Right? For instance, here I got all the pivots to be 1, but I'm not done yet because this one should be 0. Even in this case here, everything above 1 should be 0, such that the pivot is the only non-zero entry in its column. So what I did here, I divided row 3 by a sixth to get it to positive 1, right? And I divided row 3 by a sixth to get it to positive 1. And I divided row 3 by negative a third to get it to positive 1, right? You know what? We shall stop here for now. I don't actually like the method that I used here because it deals with fractions, which can easily lead me to the solution that does not match my backward substitution solution. So what I'm going to do is I'm going to open another slide. I've done this problem in another slide in a different way. So I'm going to open another new slide. I will pause this video here, and now you should refer to video 2 of my first lecture with you to complete this problem. Thank you very much for now. I will see you in video 2.